Hello and welcome to Late Night Code. My name is Ian Riley, and I'm coming at you with another problem from the North America Regional Contest. This one is called Repetitive Song. It is our second medium difficulty problem, and it is currently rated at a 3.1 on Caddis, just the same as our last one. So we are kind of moving through the medium difficulty problems. If I haven't mentioned this already, one of the things that you should be aware of is the fact that the medium difficulty is actually the smallest set of problems from that contest, which is kind of interesting. So whereas it took us a few weeks to get through the easy problems, it will only take us about a week and a half to get through all of the medium difficulty problems. The largest chunk by far is actually the hard difficulty, which again, I am really excited to get into because that's when we're going to really start being challenged in terms of our knowledge of algorithms and data structures. Everything really that we've done so far is in many ways a primer. They are giving us problems that have the right terminology, the right vocabulary, the right kind of structure to allude to classic algorithms, but they don't actually require that we use anything too extensive. Whereas we are going to definitely get that in spades when we move into the hard category. So really excited. There's going to be a lot of great stuff to learn from those problems. But before we can get there, we need to solve these ones. And so we are going to be moving on to repetitive song. Your younger sibling is obsessed with a fairly repetitive song. They claim that it is not repetitive, so you decided to prove your point by finding the longest, in terms of the number of words, subsequence of the song that your sibling cannot definitively identify within the full song lyrics. More formally, a length L subsequence of a song within words is a tuple of L integers, 1 less than or equal to S1 less than S2, so on and so forth, identifying the words in the subsequence. The subsequence is a non-identifiable, or rather it is non-identifiable if there exists a different length L subsequence, 1 less than or equal to T1 less than T2, so on and so forth, where SI is not equal to TI for at least one index I, where word S1 in the song is identical to word T1, where word S2 is identical to word T2, etc. Given the lyrics for a song, print the length of the longest non-identifiable subsequence. Input. The first line of input contains a single integer n, which can be up to 10 to the fifth, specifying the number of words in the song lyrics. Each of the next in line contains one word of the song lyrics given in order. Each word consists of up to 20 uppercase and lowercase letters. The same word may appear on multiple lines. If two words do not match exactly, including the use of upper and lowercase, then they are considered to be different words. Output. Output a single integer L, the number of words in the longest non-identifiable song subsequence. If all of the song's subsequences are identifiable, print 0. When determining if a subsequence is identifiable, treat two words in the lyrics as identical if each of their corresponding characters are identical. In other words, case does matter. Okay, so let's go and kind of break this down for us so that we better understand what's being asked, because this is one of those problems where if you're off at all in your understanding of it, you will not be able to get the right solution, and you're probably going to be banging your head against a wall trying to figure out where you went wrong. So let's be very clear with ourselves about the details of this problem. So first off, theme, what's kind of going on here? Basically, we're being asked or being told that we have a younger sibling. They're obsessed with the song that's repetitive. They say it's not repetitive. So to prove our point, what we're going to do is just give them some group of lyrics from the song and ask them if they can identify exactly where in the song we took those lyrics from. The point there being is that if we were to grab some lyrics from a song and they couldn't definitively tell us where we found those lyrics, then it would be repetitive, meaning that those lyrics would have been repeated in different areas of the song, and so they wouldn't know which one we chose. It would be ambiguous. Okay. The only requirement is that when we choose these lyrics that they have to be in the same order that they would have appeared in the song. Kind of interesting thing there, though, is we're talking about subsequences. So what that effectively means then is that these lyrics don't actually have to be adjacent to each other in the song. They can just appear in some order. They do have to appear in an order, so one must come before the other in the song. You can't just mix them around, but it doesn't actually matter if they're adjacent, so you could skip any number of lyrics that you'd like to. Now, there is kind of a caveat to that. You don't actually want to skip lyrics because you do want the longest sequence. So preferably, we would like to take everything. And if we can't take everything, we would then remove some lyrics. We can remove them from anywhere, but we want to be very conservative in what lyrics we remove. We don't remove that many. And so what we're told here is that we need to identify a number of numbers, a ordered sequence of numbers. And that's what they're using here for this term 1 less than or equal to S1 less than S2. What this basically means is that they're telling us to identify an ordered sequence of numbers. The sequence of numbers must be strictly increasing, and they must also be within 1 to n, which is the effective order of numbers of the actual input. And so what you could actually do then is you could take a song and you could then take each lyric and then you could write a number next to each lyric. And then that would be your sequence. And you can choose just the numbers. And so you could also think about S1 through SL as being like indices in a one ordered list. Okay. And so then we're told that that list of indices is effectively non-identifiable and therefore also desirable to us if there is some other list of indices where the words all match. So if we were to take one list of indices and another list of indices and line them up, then we could do a comparison between the song at each index, and they should line up by words as well. So if we were to line up S1 and T1, whatever those numbers may be, if we were to line them up as indices within the song, they would produce the same word. Okay. Now, effectively what we're told, and I'll jump over to Excalidraw to go ahead and show this, but effectively what we're told is that although these ordered sequences must line up, somewhere in those ordered sequences, they must choose different numbers. By choosing different numbers, they still have to get the same word, but somewhere along the route, they have to choose different numbers. So let's go and look at our first sample and then jump into Excalidraw to better understand what we're being asked for here. So the first sample has 10 words here, which is basically the words bow, bow, chick, chicka, chicka, bow, bow, chick, chicka, chicka, which is something I never thought I would be reading on a recording or on stream, but here we are, right? And so effectively our sample input would have n equals 10. They'd give us these 10 words, and then we could effectively assign labels to those words, 1 through n or 10 in this particular case. And so then what we could do is then choose some sequence. So let's imagine that we choose a sequence where our sequence is going to be S1, S2, and S3, and then some other sequence, T1, T2, and T3. And we'll have S1, S2, and S3 be equal to, in this particular case, I'll just choose randomly 1, 4, and 7. And then T1, T2, and T3, let's have that be 2, 5, and 8. Well, as a consequence, notice that these numbers are not the same. Okay, they're not the same, but we don't actually care whether or not the numbers are the same. We'll get to that in just a second. What we care about is whether or not the words are the same. So if I were to line these up, notice that 1 and 2, this would be the same as basically saying something like the song at S1 is equal to the song at T1, and this would actually be correct. So notice that if we were to look at the song at S1, our song at S1 is going to be the first term because S1 is 1, so it's going to be bow. And then our T1 term is 2, and the song at 2 is also bow, so these are actually a match, so that's fine there. I'll go ahead and do that in green. There we go. And now if we were to move on to the next one, so since that's fine, we have to move on to the next one here. And so then we would ask the question, is the song at S2 the same as, I'll use a double equals, the song at T2? And what happens there is that S1 is 4, which is chicka, and T2 is 5, which is also chicka. And so those are actually a match. And so we have a match there. And so we continue. And so then that brings us to asking the question whether or not the song at S3 is going to be the same as the song at T3. And the song at S3 would be 7, so that's going to be bow. And T3 is 8, so that's chick. And so these are in fact not the same. And so these ordered sequences would actually fail a fundamental requirement of the problem, which is that the numbers in the ordered sequences, when those sequences are lined up, actually do produce the same words. Okay. So an easy way, of course, to fix this would be to go ahead and just take T1, T2, and T3 here and just rewrite them. So that way, let's go ahead and just say something like 1, 4, 7, right? If I want to guarantee that they're the same words, why don't we just choose the same sequence? And so that gets us to the other part of the problem, which is that at least one of these must be different. Okay. So if we're now to kind of summarize what we've learned from this, then we can say a few things about this particular problem. We can say, for example, that we need sequences of words, okay, that both, misspelled both there. that both sequences must match. And that number 3, that effectively one of the sequences has to get the same word from a different position. And so what that means is that the sequences use different indices. And then we'll just put a little note there, not all. Okay. So effectively, again, so we have sequences of words from the song. 2, both sequences must match. That means that the sequences of words themselves must be the same, so they must appear in the same order. And then but 3, that they would use different indices, so that one of the sequences must get the right word from some other position. And so we can go ahead and just quickly kind of look at one other thing, which is, of course, what's most desirable about our output, which is the longest such sequence. So what would that mean? How can we take these ideas then and actually then relate them to the idea or to the question of longest such sequence? Well, let's just go ahead and use a very rudimentary example, and let's just go ahead and say that we want to have our first sequence S1 be S1 all the way through Sn. So effectively what this would require then is that we would be taking all of the terms in the song, so all of the lyrics, okay? Well then, if I were to take T1 all the way through Tn, hopefully we can both agree that if I go ahead and look at the cardinality, okay, of these particular things, then we are in fact going to get 10 length. So basically both sequences are of size 10. They both have the same sequences. They both have the same number of words, but there is a problem. They don't use different indices, okay? So one thing we can go ahead and just quickly identify is the fact that there is going to be effectively no solution of n, right? The largest solution is n-1, the smallest solution is 0. So that basically means that we're working between 0 and n-1. Okay, so somewhere in that effective range is the range that we need to look at for our potential solutions. Okay, so now that we kind of understand the basics of this problem, let's start talking about how we could actually go about solving this problem. Well, one thing to quickly note about this problem is it has the but it has some of the signs of a classical sequence matching or string matching algorithm, which is called sliding window. And so effectively, one of the ways you could think about this problem is that you might take some amount of data from the original song list and then try to compare that window of data to another window of data. This kind of has the aura, if you will, of a variable length sliding window. There is, however, one kind of problem with that approach, which is that we're not being asked for consecutive terms, but actually just sequences of terms, which means that you would also have to be aware of the fact that your effective window might have to then be attached to other windows, which is not really what sliding window is about. We'll cover that particular algorithm in a later video, but I just want to go ahead and note that it has some of the markings. Now, the reason why I bring that up, even though we know that we're talking about sequences, is because there's something really interesting about this problem that actually can kind of put it back into the same space of a sliding window, which is effectively to think about this problem not so much in terms of its windows, but actually in terms of its partitioning. So what do I mean by that? Let's go back to this idea that we have here, where we wanted to grab every single term. Well, why is it that we want to grab every single term? We want to grab every single term because it absolutely guarantees the longest sequence, right? That's how you get the longest possible sequence, is you just take everything. But we can't do that, of course, because we have to have at least one index that's not matching. But there's the important thing, though, about this revelation, if you will, about why this particular approach wouldn't work. The revelation is that it has to have one index that doesn't match. It doesn't have to have more than one. It has to have at least one. So if we can't go for n, what is the solution that we should be trying to go for? We should be trying to go for n-1, right? That's the longest such sequence where we don't take that at least one, right? Well, so what would that mean for us if we're only going to take, or rather if we're not going to take one of those terms? It's, in other words, kind of like trying to figure out which of the 10 terms here we don't take, and that would give us our n-1. That's another way you could think about it. But kind of an important thing, though, there about these two sequences is if they have one term that's not the same, what does that mean for all of the other terms? It means that all the other terms must be the same. So that's where partitioning could come in. You can, in some sense, if we were to line up here, right, and if I were to go ahead and take my blue again, and if we were to line up S1 all the way now up to S of n-1, then what that means is that somewhere in there, there's this SI term. And then we'd have T1, and then we'd have a TI term, and then we'd have T of n-1. And so we'd line those up. And what would that mean when we line these up? Well, one of the things that it would mean is that S1 and T1, all of these should be matching words, have to be, but also they could just be the same numbers. Okay, they could just be the same numbers. Then we'd have SI and TI. Now, SI and TI are absolutely not the same number. Okay. And then we'd have SI plus 1 all the way to S of n-1, and similarly for T of I plus 1 to T of n-1, and they might be, but are probably not, the same words. And so one of the things that you can actually see here is that effectively SI-TI, or I said words earlier, I meant numbers, but SI-TI are definitely not the same number, but they are the same word. And if they're not, then it must be the case that either their prefix, right, would have potential differences, or their suffix would have potential differences, even though they would be the same words. Okay. So the way you could think about that is, let's take this idea and bring it over to this particular problem with bow, bow. Okay. So let's imagine here that we're trying to find a particular case where we could have both the prefix, the TI-SI, and the suffix, and see what that would mean for this particular problem. And what I want to draw your attention to is 6 and 7. Okay? Because we can see here that both of those words are the same. Okay? And so imagine then that what we do is we create a prefix from 1 through 5, where S1 through S5 and T1 through T5 are all the same here. So this is S1, T1, all the way to S5, T5. We have a matching prefix, both in terms of words and indices. And then we go ahead and take number 6, and this is going to be S6. And then we'll take number 7, and we'll have this be T6. Now notice that they're the same word, but not the same numbers. And then we're going to go ahead and take this right here, and this will be S7, T7, all the way through S9, T9. Okay. Now notice that this is actually even stronger of an example than what I had mentioned earlier, or alluded to earlier, which is that in this case, we'd actually have a prefix where all of the same numbers are used, and a suffix where all of the same numbers are used. And what's interesting about this problem is that this is actually guaranteed to give you the longest such sequence. Now, the reason why this is guaranteed to give you the longest such sequence has to do with this concept of S jumping over T. Okay? And so a way that you can kind of break this idea down to understand why this would work is, let's go ahead and imagine, I'm going to go ahead and use the terms. I don't want to use S again, but we'll just use X. So you have X1, X2, and then I want to go up all the way over here to some Xi and some Xi plus 1, and then that'll go all the way to X of n. Okay, so these are all of the words in our song. So I guess L would technically be better here, but L is already used in the problem. And so what we want to do then is we want to line up indices from the ordered sequence of S with these X's, and indices from the ordered sequence of T with these indices. And so what I'm going to do here is I'm just going to go ahead and say that Xi and Xi plus 1 are effectively like that example that we saw with bow bow, where they're two adjacent words that happen to also be the same. Well, what happens then is I'm going to go ahead and take everything from X1 to Xi as S, And then I'm going to go ahead and take everything from x1 to xi minus 1 as t. And then I'm going to go ahead and take xi plus 1 to xn as t. Well, now s can't take xi plus 1, right? Because if it does, it's not guaranteed to be able to line up with t. So what's the next term that should appear in s such that we maximize the length of the sequence, but keep the words the same? Well, the best way to do that is to just go to the very next term in t after xi plus 1. Okay? Because again, if xi and xi plus 1 are the same word, if you jump further away, then you're just reducing the size of your sequence. The next closest word that gives you matching sequences is the word that comes right after xi plus 1 in this case. So if xi and xi plus 1 are the same word, and you want to maximize the length of those sequences, you just take the word right after xi plus 1. That's effectively how you do it. And if we were to then consider that this sequence of x1 were to now be disparate in the term of, it would do like something like x2, then xi, and then some xj, so this now being a more general case, then we can still do the same thing here, where we would take x1 through xi as s, and then we would go ahead and take everything from x1 to xi minus 1 as t, and then we would go ahead and take xj through xn as t. Again, this is maximizing the length of t. So then how do we go about maximizing the length of s? Well, we just once again need to jump right after xj to xj plus 1 and take that as s. That's what maximizes the length of s and then matches the length of t. The only other choice that you could potentially have is somewhere between xi and xj, and somewhere between xj and xn. But note, really quickly, we can see that if we choose between xj and xn, then we're just shrinking s. So that's just going to make a smaller sequence. Now, if we could choose between xi and xj, then we could potentially get a longer sequence. So I can go ahead right here and think about choosing s somewhere here, right? And so this could potentially result in a longer sequence. But now note that that sequence, the size of it, if we were to take the size of s, how does it compare to the size of t? It's larger. It's not the same length. So effectively what happens is we would then need to go ahead and trim off on the outside to make sure that the sizes of s and t match, because we can't make t any bigger here. Okay. Now you might wonder, well, okay, why can't we make t bigger? Can't we also just choose somewhere in here for t? Well, one of the assumptions that we have to make here, that's an important distinction, is that if x and I matches xj, then we have to make the assumption that xj is the next word after xi that matches xi. So effectively what we're going to go ahead and say here is that if we were to presume that there exists some k such that xi is equal to xk, then it must be the case that k is greater than or equal to j. So j is the very next word in the sequence that matches xi. So there is effectively no way to choose another position for t in that middle ground. And so therefore t is the largest it can be. And therefore we can't choose one in the middle ground for s, because then s would just be strictly larger than t. So the next best thing to do is just to choose the next term right after xj. Oops. And that's effectively how we could break down this problem in probably too many words. I need to get better at explaining these in more concise detail. So maybe later in the summer when I have more time for a prep, I'll be able to do that more effectively. I'm also just kind of enjoying like going through the problem. This is the part of the really fun thing for me, is actually like working through the problem. I love programming, but in some ways it can sometimes be secondary to actually just working through the solution on a board. I don't know, maybe that's probably why I'm an academic, right? Because I really like being on the whiteboard, or blackboard in this case. Okay, so the last thing I just want to go and note here then as part of the discussion of this problem is that we have one singular thing that we're interested in with this problem. And the way that we can phrase that thing is just to go ahead and say that what we're interested in is minimizing what I would like to call jump distance. Okay. So if you want to maximize the length of the subsequences, you need to minimize the distance that you would jump from some xi to some xj plus 1. So effectively, minimize the jump that S has to take going from one side of S to the other. You minimize the jump distance and you will find the maximum length subsequence for your repetitive song. The other thing, I said the last thing. I always say the last thing. I always like two more things. But I didn't mention what happens when there is no jump distance. So what happens if the jump distance effectively like is infinity or not a number, it just doesn't exist. The reason why a jump distance wouldn't exist is if all of the words are unique, meaning that there's no word that has a duplicate or a repeat in the sequence. And we've already been told what the solution here is. We're just told we need to output 0. So that's effectively, there is effectively no sequence to look at. So the length is 0. And with that, I think we're ready to go ahead and jump into this problem and actually give it a solve in Rust. So the first thing we're told is we're given an integer input. So n, this is effectively a usize. So we'll go ahead and say let n be equal to next turbo fish into usize. And then we'll go ahead and pass in a mutable reference to a buffer. And then I'll go ahead and define that mutable buffer because we're going to be grabbing lots of words here. So after we have n, then the next thing that we're going to go ahead and do is just go ahead and iterate over all the possible positions. So we would say for I in 0 to n, which are positions here. I'm not going to worry about doing a 0 order. And so then I need to go ahead and get the next word. So we'll say buffer.clear, and then we'll go ahead and say let lyric be equal to next. And then we'll say here turbofish into string, and we'll pass in a mutable reference to that buffer. And now I've got my lyric and I actually know which word I'm looking at. So what would I do then to be able to retain the position of this word? Well, the best way to retain the position of this word is to come up here and go ahead and access collections. And you guessed it, hash map. And so then now with that hash map in place, we can go ahead and say, we need to define a hash map, of course. So let lyrics map, which needs to be, in this case, mutable, be equal to a hash map new. And then we'll come down here and now we can go and say lyrics map dot insert lyric at I. And so now that will actually insert the lyric into I. Now that we've inserted the lyric into I, what happens whenever we have a duplicate? Well, one of the things that would happen if we have a duplicate is we'd actually overwrite the integer position associated with that lyric. But that's okay because once again, when we're talking about minimizing a jump distance, we always want to take the rightmost position because if you think about it, when we find a duplicate, okay, we don't want to compare the duplicate to some leftmost position because that's just an absurdly large jump. We want to compare it to the next position, the rightmost position that we found so far, because that's what's going to minimize the jump. So effectively what happens is we scan over the words, taking the rightmost position, and that's going to guarantee that when we find duplicates, we're always producing the smallest jump distance for that particular duplicate. Which then brings me to the idea that, well, maybe we do in fact have a duplicate. So we can go ahead and say match on lyrics map.get, passing in a reference to lyric. This is either going to come with some position here, so we could say some j, or it's going to come back as none. And if it comes back as none, we just effectively don't care. But if it comes back as j, then what that means now is that we can go ahead and compare the distances between j and I, keeping in mind that I must be strictly larger than j. I do want to effectively take this as a reference. There we go. And so then now what we would need to go ahead and keep track of is our mutable min jump, which will go ahead and start off as a U32 maximum. Okay, so we'll just go and store that. In fact, actually, I don't need to do U32 and show you usize. Perfect. Okay, and so then from here, what we can go ahead and say is that our min jump is now equal to our comparative minimum of min jump and I minus j, which also means that I'm going to need my comparator. Perfect. Okay, so we'll go ahead and try to fetch the lyric from the lyrics map. If we in fact have some position associated with it, then that's some prior position. So now we can go ahead and say that our minimum jump distance is the minimum between our current minimum and the difference of these two indices. If we don't have anything, then we just don't care. We move on, and then we go ahead and insert something into this. Then at the end, there's only a couple things that could happen. The first thing that could happen is that min jump could be equal to our usize max. Now, what would that mean? That would mean that everything is unique. We never found a duplicate. So we can go ahead and say print line and then just print 0. That's effectively our solution. Otherwise, we actually did find some duplicate. And so now we can go ahead and print off our solution, where our solution is n minus the minimum jump. Okay, and that one is looking pretty good. So then with that, let's go and open up a new window here. Let's go ahead and make that just a little bit bigger. And I'll go ahead and copy our first sample. Now, repetitive song did not actually come from Southeast. So you can see here, oh, I misspelled. But you can see here it doesn't exist. It came from, I think, North Central. And so we don't have access to those test cases. But I can go ahead and grab this sample here. And then we can go ahead and clip key into cargo run --s and then do repetitive song. And we see we get a 9, which is exactly what we're expecting. Then we'll take the other one. We'll do the same thing. And we get a 29, which is, again, exactly what we're expecting. So from here, since we don't have any test cases, the next thing for us to do is just go ahead and upload that to Caddis. Upload that, and let's go ahead now and submit. Okay, and we've successfully passed all of our test cases on Caddis, and we have another problem knocked out. Hope that you really enjoyed this one. If you have any questions, please let me know in the comment section below. I'd be more than happy to answer them. I've had a great time with this. Arguably, it's probably spent too much time in the discussion, but hopefully it was enjoyable and educational, and that you learned something from the solution. So hope you're getting excited. I certainly am. More problems to come, but until then, have a great night.